This tutorial would like to give some recommendations for finding a suitable encoder for your application. It focuses on incremental encoders, the most widely used sensors for speed and position feedback on miniature motors. Additional information on the different maxon motor types and their applications can be found in the maxon encoder families video. There are several types and technologies of incremental encoders, but at the end they all give the same type of rectangular output signals. The characteristic parameter of incremental encoders is the number of counts per turn on each of the two channels A and B. This number can vary from about 16 up to several thousand. Typical values for many applications lie in the range between 100 and 1000 counts per turn. The actual resolution is 4 times higher because there are 4 states per signal periods. These are called the quad counts or increments, or often referred to as lines per turn. However, the wording is somewhat ambiguous, and when talking about encoder resolution, you have to make sure whether it is meant before or after quadrature. The required positioning accuracy of the application dictates the resolution of the encoder. A general rule states that the measuring system should have a 4 to 10 times higher resolution than the required accuracy. Hence, the encoder resolution given in counts per turn should at least be equal to the required resolution. The quadrature will then guarantee that there are enough states to obey this rule. Observe, encoders are mounted on the motor. A gearhead reduction increases the resolution at the load by the reduction ratio of the gear. Therefore, in combination with gears or other mechanics, encoder resolution hardly ever needs to be higher than about 256 counts per turn. In addition, be aware that the mechanical play usually makes any higher resolution useless. On the other hand, high-resolution encoders of more than 1000 counts per turn are often used in direct drives. For the following, we focus on motors alone, assuming that the required resolution has been calculated back to the motor shaft level. The previous general rule states that the encoder resolution n in counts per turn should be higher than 360 degrees divided by the required positioning accuracy delta phi in degrees. For instance, an angular accuracy of 1 degree requires an encoder resolution of at least 360 counts per turn, resulting in a measurement resolution of 0.25 degrees. For high dynamic applications with fast controllers and low permitted position overshoot, select a higher encoder resolution. However, be aware that with too high an encoder resolution, the signal frequency increases and the signal-to-noise ratio may be worse. Further recommendations. Whenever possible, use an encoder with line driver for positioning. This differential signal transmission avoids pulse losses and gives you a better signal, in particular over longer distances. Many encoders have a third channel, the index channel. It can be used for precise homing. It is finding a more accurate reference position than with the classic limit switches alone. What is the optimum encoder resolution for speed feedback? This question is not that easy to answer. There are many influencing factors. So what can happen to speed within one sampling period of the speed controller? Friction and load variations can lead to a deviation from the actual speed level. A high mass inertia, on the other hand, dampens this effect. The big question is, how much deviation is allowed and how large are the friction and load changes to be expected in relation to the damping effect of inertia? A high sampling rate of the controller and a suitable speed control architecture, for instance with a speed observer, can help to keep speed variations small. These considerations show that it's not the encoder resolution alone that defines the quality of speed control. Mechanical aspects such as friction, mass inertia, as well as controller properties are important. However, what are the main considerations regarding encoder resolution in speed feedback? In the speed controller, velocity evaluation is usually done by counting the number of states per cycle time. At a reasonably high speed, there are many states per cycle time. A typical example could be motor speed 2600 rpm, encoder resolution 256 counts per turn, which corresponds to 1024 states per turn, and a controller sampling time of 1 millisecond. This results in about 44 increments per millisecond. The quantization of speed measurement is 1 increment per millisecond, corresponding to a speed resolution of 58 rpm, or a little bit more than 2% of 2600 rpm. The situation looks different at low speeds or at lower encoder resolution, however. In the same millisecond, there are less increments. The resulting speed resolution is still 1 increment per millisecond, but this corresponds now to about 9%. A similar effect is obtained by a faster sampling. There is a tendency towards faster sampling times in modern controllers. And we have seen on the previous slide that for narrow speed tolerances, faster sampling is a good thing to do. However, for the same speed and the same encoder resolution, there are less increments and the resulting speed resolution will be lower. All this leads us to the following conclusions. The lower the control speed, or the faster the controller, the higher the required encoder resolution must be. Controlling low speed with a fast controller needs very high encoder resolution that can easily reach several thousand counts per turn. At high or very high speed, on the other hand, a lower encoder resolution might be selected. Just verify that the encoder supports the high mechanical speed and that encoder and controller can handle the high encoder signal frequency. Let's have a look at the maxon encoder datasheet. Where can you find the information that we have been discussing? As an example, we take the configurable ENX16 easy encoder with a resolution of up to 1024 counts per turn. The key data give general information such as number of channels and maximum possible counts. The number of channel 3 indicates that there is an index channel in addition to channels A and B. From the designation differential in the black bars, we can conclude that there is a line driver available. Indeed, the 3 signal channels with their complementary counterparts can be found in the specifications part, more precisely on the right in the pin allocation. Additionally, the specification gives information about supply voltage range and maximum speed and operating frequency. The configuration shows the range of resolution and possible cable lengths that can be selected. That's it, a short introduction to encoder selection. In summary, it's not always the highest encoder resolution that gives the best result. Look exactly what your application and your feedback loop requires.